Hello everybody, welcome back to the video. In the last video, we talked about the neural model optimization. So basically, just try to demonstrate how we train the neural model and how we update the weight, the bias of the model to minimize the cost function. And as one key part of the training is to get the gradient. And how to get the gradient of a neural model is the foundation of the so-called backpropagation method. And the chain rule is the foundation of the backpropagation. And in the last video, we actually briefly talked about the single variable chain rule in the simple example. And when the neural model has multiple perceptron and multiple layers, the single variable chain rule cannot be used to explain the gradient clearly anymore. And in this situation, we have to introduce the multiple variable chain rule, and which will foundationally will be same as single variable, but the form will be much different. And we will introduce the difference and demonstrate the relationship between the partial derivatives of the different layers in this video. And we will start with a very simple example. In this example, we have a few functions. And the first functions, z is a function of x and y, x is a function of r and s, and y is a function of xs also. And meanwhile, we have r is a function of tp, and s is a function of tp also. And the reason we have this multiple variable function is simple, because it looks like the plain old neural model. Of course, there's a lot of multiple variable functions. We just limit our discussion in this form, which is similar to the neural model. Of course, even for neural model, there will be different structure in the future, but this one is the foundation. So we will start our discussion with this one. And usually, people call this fully collected forward network. And how can we demonstrate this function has a similar feature as the fully collected forward network model? And we will use with the help of something called dependency diagram. Dependency diagram is very simple. We just write the dependency between the variables according the functions. For example, in this example, we have the multiple variables z, x, y, r, s, t, p. We just write the relationship according to the functions. You can see z dependent on x and y dependent on r and s dependent on t and p. Just look at here. You can see it's very similar to our neural model. When the neural model has multiple output, but as we introduced in our notation video, eventually you will only have one cost function. In this situation, we can think z is a real starting point, which is a cost function. Then there will be different layer in this dependency diagram. And in this discussion, we just simply call it z is layer 0, xy is layer 1, rs is layer 2, tp is layer 3. So when we try to get the gradient for the backpropagation, what we need to do to get the partial derivative of the const function with respect to the weight and the mass. And here, so similarly, we will try to get the relationship between partial derivative with respect to x, with respect to r and t, between different layer, and so on. So we try to find the relationship between the different layer, and which will help us to understand the backpropagation method. So we will start from layer 1 here. So in the layer 1, it was just simple calculation, partial z with respect to x, partial z with respect to y. And for the layer 2, we will use a help a little bit from the dependency diagram, when we need to get partial z with respect to partial r, partial z with respect to partial s. So we have different paths in this diagram from z to r, from z to s. For example, from z to I, we can from z, x, r, and also we can have z, y, r. So we can get two items to get the partial z with respect to partial r. Similarly, in order to get a partial z with respect to partial s, we also has two paths, which is z, x, s, z, y, s. If we observe it, basically it's from top to bottom, from left to right. You just follow this convention, it will be fine. And after we finish this, and we observe a relationship between the layer 1 and the layer 2, we actually can write this in a matrix format to describe the relationship of partial derivative between layer 1 and layer 2. This one is very simple, and because it only have one layers. This one is very simple, and we write it in a vector and multiplication of the matrix format. We can see this is a Jacobian matrix. And in order to construct this Jacobian matrix, it's very simple. You just from top x to bottom r and s, and from left r to right s. Then you can construct this Jacobian matrix easily. We just name this Jacobian matrix between layer 1 and layer 2. And this Jacobian matrix form a collection between the layer 1 and the layer 2 partial derivatives. Layer 1 and layer 2 is comparatively easy. Now let's talk about layer 3. Layer 3 will be a little bit busy here, and the idea is same. In order to get partial z with respect to partial t and partial z with respect to partial p, and we have to go through all the paths in the dependency diagram. So basically for t, we can see you can go from z, x, r, t, and also you can go from z, x, s, t. The third path will be z, y, r, t, and the fourth path will be z, y, s, t. So you have to write all these partial derivatives with chain rule, and we will use all the paths to write all the product of the partial derivatives on the path. So we will get the partial derivative of partial derivative z with respect to t and the partial derivative of z with respect to p. And we will take some time to write the whole results here. So after we write all the paths to get the partial derivative from near 0 to near 3, we observe this and also depend on the knowledge we get from the forms of near 2, we can guess. We can think this could be a near 1 partial derivative multiplied by the near 1 and near 2 Jacobian matrix, then multiplied by the near 2 and near 3 Jacobian matrix. We will write the formula here. So I will do it slowly to show everything here. Just want to make sure you have time to look at how it's done. A lot of time when we learn something, our brain think we know it, but when we try to write it down, we find out we actually didn't quite get it. So my suggestion to the viewers here is, if you cannot follow this, just find a piece of paper and do the calculation yourself. It takes some time, but once you get it right, you will confirm your learning your brain using your hand. That is very helpful. Now here we write the layer 0's partial derivative with respect to layer 3 using the near 1 partial derivative and 2 Jacobian matrix here. Of course, and we can also write it as layer 2 partial derivative multiplied by the Jacobian matrix between layer 2 and layer 3 as following. So after write this way, and you will ask, people will ask, how can you prove this? I mean, I just said, this is, you don't need a proof. Just find a piece of paper, expand the form I guessed, and you can see it hold. It means the Jacobian matrix relationship between near 1, 2, 3 is just like the relation between near 1 and 2. It is connected by a Jacobian matrix. So here we just expand the calculation of the vector multiplication in the matrix. And as I suggest, find a piece of paper and write it down. You will see the relationship is good. So when I write this to prove this relationship, I just want to tell you why we have to do this. Because the back propagation is whole thing is about how to get the partial derivative for the next layer. So from here, you can already see something of that. Once you get the partial derivative of layer 1, and with the help of a Jacobian matrix, you can get the partial derivative of next layer, vice versa. And I've already watched a lot of examples. People just use one number to go with one path. And here we try to do a general thing we give you a form which is the vector multiplication of a matrix with Jacobian to establish a relationship between the partial derivatives of the between the positive of different layers. And when you try to derive the back propagation, you will have a better understanding, since in order to use back propagation, eventually everything has to be in vector and matrix form. And the single pass number is not very easy to use. And the other benefit is, if you learn everything in the matrix form, if the structure changed, you can in your brain just change the Jacobian matrix, then it will be easier for you to expand your knowledge in the future. So here I just there's no theory here. I just do the vector and the matrix multiplication, write out the layer 3's partial derivative, and we can see after I did the multiplication, it's same as what we just simply write out using a different path. So after this, we kind of know that for this type of network, their partial derivative between different layers are related by a Jacobian matrix. And the summary of this video will be the Jacobian matrix. The Jacobian matrix connect the parent layers and the child layers partial derivative give you a good relationship. So once you know the parent layers partial derivative and you know the relationship, you can use a Jacobian matrix to get the child layers partial derivative. And the other thing we learned from it is, once you have this relationship, you can see the different layer is the relationship is built on the Jacobian matrix. So if your relationship between the child layer's relationship between the parent relationship, the network didn't change. Whatever changed above the parent layer won't affect this relationship. This is very good property. And this pretty much is all about this video. We talked about the neural network chain rule for the multiple variable. And we demonstrate for a fully collected forward network, the partial derivative between different layers can be connected by a Jacobian matrix, which everybody is familiar with. And this feature can be easily used in the backpropagation method. So in the next video, we will talk about in detail about this Jacobian matrix and a few special form of it. And we will step by step to get closer to the final derivation of the backpropagation. Thanks a lot for your time and I hope to see you in the next video. Thank you. Bye.